All right, I'm back. We are on page 289, and what we're going to do is just continue our discussion, right? So there's some notation, there's a lot of thinking, there's a lot going on, right? We're talking about derivatives. Derivatives are slope, the slope of the tangent line. Where do derivatives come from? They come from taking the limit of the secant line as the 2 points approach each other, right? That's basically what it is. So let's see if we can write down the slope of a secant line using the points x f of x and a f of a. So x is some generic x value and a is a specific value. So a is like 6 or negative 52, wherever you're trying to find the slope. So our secant line slope will be f of x minus f of a over x minus a. All right, so not really the place for it, but this is just algebra 1 slope. Algebra 1 slope has another name. So algebra 1 slope equals the average rate of change. Excuse me. So it's the average rate of change. It's the rate of change over an interval. On average, how much does the function increase? It increases however much it changed by however far you went, like delta y over delta x. Algebra 1 slope, average rate of change. Every time you hear average rate of change, say algebra 1 slope. Every time you see algebra 1 slope, think in your head, that's average rate of change. If you can get that straight right now, forever that's going to help you out. So average rate of change is algebra 1 slope. It's really just the difference quotient, right? So that's a quotient with a difference. This is the difference quotient. It's not just a difference quotient. This is it. This is the difference quotient. So if we let the 2 points get closer and closer, right? So we let x approach a, right? Because a is fixed. We let x approach a. Our secant slope turns into our tangent line slope. So that's what we're going to do here. And I'm going to write that down. So the limit definition of the derivative at a point is going to be, so we'll say f prime of a is the limit. I want x to get closer to a. Always think in your head, like what is getting, sometimes we have something getting smaller, other times we have things getting closer together. In this case, we have the 2 points getting closer and closer together. Let me draw a little picture. So also my chair now squeaks, so that's great. It's like it wasn't meant for this much sitting, but who knows? Right, we have this. Here's our point a comma f of a. And then here's our point x comma f of x. It doesn't really matter what side it's on, but you pretty much always draw it to the right, you know? And what's going to happen is we're going to let this point move closer to this point, right? So we want x to approach a. And as x approaches a, the secant line turns into a tangent line. When x gets to a, and they're exactly in the same place, it is the tangent line. So that's what we're doing here. The limit as x approaches a of what? Of the slope between those points. That'll be f of x minus f of a over x. Oh my gosh, what happened? I got you. X minus a. That's it, okay? You're going to memorize that. You're going to remember it forever. But it's just slope of a secant line, right? Change in y, which is f of x minus f of a, over change in x, which is x minus a. That's slope of the secant line, average rate of change, algebra 1 slope. And then we let x get closer to a. We just slide along the curve where the secant line transitions from a secant into a tangent. So there you go. Also, you may remember when we were doing like 14 formulas and all that, I kept saying like everywhere there's a secant, there's a tangent. Secant and tangent come up all the time together. Like this is another place where a secant line turns into a tangent line. Happens a lot. Secant and tangent. Some kind of secret relationship going on there. There's another form of this that I think is actually more common, right? And it's, I'll draw the picture again. Instead of calling the points, well, all right, let's just draw it, right? So this will be the point A, f of a, and then this will be the point, I forget what colors I'm using. It doesn't really matter, but can I move you? Yeah. So this is going to be a plus h, f of a plus h. Okay, and then our goal, again, is to let that point, the second point, slide toward the first one. So we're going to slide down the curve like so. And then how do you make it slide down the curve? You don't want x to approach a in this case, because that doesn't really make any sense. But to get a plus h to be closer to just a, I basically need h to approach 0. If h approaches 0, then the slope of this secant line will become the tangent line. So let's do that. We're going to say that f prime of a, the slope at x equals a, is the limit as h approaches 0 of f of a plus h minus f of a divided by h. That's another form of the limit definition of the derivative at a point. So these are at a point. They will give you numerical values when you use them. And that's like, this page is just like a lot of defining things. So we have these two different things. If you don't have these memorized, you're going to be in trouble. Like you're just, that's like, that's time to drop out, right? So you have to have those two things memorized. You got to bring them with you to the calculus fight. If you don't show up with your definitions of the derivative, you're doomed. So we have, I call it the x approaches a definition, and then the h approaches 0 definitions. Whatever, they're just two different definitions. You got the limit as x approaches a, f of x minus f of a over x minus a. Memorize that, say it 1,000 times. 1,000's probably enough. And then you also have f prime of a as the limit as h approaches 0, f of a plus h minus f of a, all divided by h. So that's like the over h one, or using h. That one's more common. So the first one is faster. When we actually calculate them, you'll see that that is a faster definition to use. The second one, on the other hand, just one. It's like the most common one, right? So, you know, there's like, I don't actually know who won this battle at this point in time, but there's like Windows and there's Mac OS. They're like two things, basically do the same thing, just preferences, whatever. We have two different definitions that'll give us the derivative at a point. Little terminology. If the derivative at a point exists, which there are places where it doesn't, we don't know any of those yet, but if the limit exists, when we find these limits, so limit existing means the limit from the left equals the limit from the right, doesn't have to equal the value of the function because we're not talking continuity, we're just talking the limit from the left equals the limit from the right. If the limit exists, that means a function is differentiable. So differentiable at a point means that f prime exists at that point, the derivative exists at that point. If a function has a derivative at a point, we say that it's differentiable at that point. Eventually, we'll see things where that doesn't work out. And then the first application, the first real application that we know is that a derivative tells us the slope of a curve at a point. So we can now find the slopes of curves at specific points. That's a really big deal because we're going to find applications. If you have a position function, the slope of position is going to turn out to be the velocity of that thing. And that's a crazy connection. And there's just an infinite amount of other connections that we can make, but like that's going to be the most direct one that we make initially. But anyway, I'm going to wrap this here. I will come back and we will just keep doing more. So I hope you're excited about this. I hope it's making some sense. If it's not, ask questions in the comments, in the documents, in class if we're having that. However, ask your friends. You just want to make sense of this because it's like this really amazing concept, and the more you get it, the more it like weaves together and reinforces itself. So I'll see you in the next video, and I hope you are enjoying these. So yeah, see you then.